All right, everybody. Good afternoon. Okay, questions, issues, moans, whines, complaints about the homework.
Yes.
Speak to me.
Numbers 14, 16, 25. Yeah.
Okay. I don't have my document open in front of me. Can you tell it to me? What's 14?
Infinite sum of n over square root of n squared plus 1. Yep.
Okay. All right. So, and you're told to use the direct comparison test or what?
Just verify if it diverges.
Okay. Well, you can do this by just looking at the limit as
Yeah.
n approaches infinity. You wind up with, you get infinity over infinity, right? So you use L'Hopital's rule,
Yeah.
and that gives you 1 all over 1 over 2 square root n squared plus 1 times the derivative of the stuff inside, which is 2 over n, right? So the 2's cancel, and you wind up with the square root of n squared plus 1 all over n, right? Now, if we look at this, I mean, well, first of all, we're going to learn a test today that's going to make it really, really easy to do. But you can do this. This is the same thing as saying the square root of n squared plus 1 all over n squared, which is the square root of 1 plus n 1 over n squared. And then as the limit goes to infinity, this goes to 0, and you just get 1, which means that the limit is equal to 1, right?
Yeah, so it diverges.
So it diverges, because basically after like a billion terms, you're adding 1 plus things that are really close to 1 plus 1 plus 1 plus 1 plus 1, and eventually it just goes off to infinity.
Is the way I did it okay? The way I did it was I multiplied the top and bottom by 1 over the square root of n squared. Because then isn't
Yeah,
this...
that would have gotten you to do the same thing,
Yeah.
You're, um, and this numerator obviously goes to 1, and your denominator becomes
The same thing that was on the bottom.
right,
Yeah.
which goes to 1, which is 1. Yeah. So yeah, number 16.
N factorial over 2 to the n.
Okay. And it just said converge or diverge, right?
Verify that it diverges.
Verify that it diverges. Okay. Well, let's look at this for a second. So let's look at some n squared. Let's look at n factorial for. Let's look at both of these terms for a few steps. So n factorial 2 to the n. And now you can say, when n is 1, you have 1 factorial and 2. 2 factorial is 2 and 4. 3 factorial is 6 and 8. 4 factorial is 24 and 16. 5 factorial is 120 and 32. Now, what you can say from here is that after this point, okay, for n greater than 3, n factorial over 2 to the n is greater than 1. And so you can say that well, actually that, yeah, just the way you would write it. And then you would say, since of 1 diverges and n factorial over 2 to the n is greater than 1 for n greater than 3, then this also diverges. Factorials grow really fast. They're like super crazy fast. Okay. So if you see a factorial, it's probably gonna win in the tug of war of the numerator denominator fight. So you just needed to show that there was something that was underneath it that was also going to diverge.
Yeah, all right.
Yeah.
And so
You
yeah,
could have done it in any number of ways, you know, but all you really need to say is that there's something smaller than n factorial to over 2n that diverges. So you could have used like an infinite geometric series, right? You could have said, you know, you could have looked at 3 over 2n, right? Well, this is less than n factorial over 2 to the n because 3 to the n is less than n factorial after some point, you know, and 3 to the n is 3, 9, 27, 81, and you got to go a little further, 243, but after a certain point, the factorials are going to win. Actually, the next step is going to win because the next step is 720. And the next one after here is brain damage. 729. No, it doesn't. The next one would, though, because you're only multiplying by 3 on the next step, and you're going to be multiplying by 7 on the next step after that. You see what I mean? So really, that's the whole idea about the comparison test, is find something above or below that converges or diverges and use that to show that, to force to say that, I'm either in this kind of a situation, this guy diverges, so therefore this guy diverges, or you're in this kind of a situation where you're saying this guy converges, so therefore this guy converges. That's the whole idea. Okay.
oh, okay, so 25 would be 1 over, so it's -1,
Yeah.
-1 over, to the power of n, over n factorial. And so on this one, you would say like 1 over n squared.
Well, this is the alternating series.
Yeah, yeah.
Okay. So
like you would separate the -1 over.
actually,
or
all you have to say is that the limit as n approaches infinity of the absolute value of -1 to the n all over n factorial. Okay. Now, when you take the absolute value, this numerator just becomes 1, always, right? So and the factorials are always positive. So now you can say that, and this goes to 0. So by the alternating series test, the series converges. Now, if you wanted to use something other than the alternating series test, that's not hard to do either, because you could just say, oh, there goes my ruler. You could say that this converges, right? And well, because that's the same thing as, and that's a converging geometric series because r is equal to -1/2, which is which is less than 1 and greater than -1, right? So this converges, and you could say that 2 to the n is always 1 over 2 to the n is always smaller. Great, brain damage. It's always greater than 1 over n factorial. Once you get past, after n is greater than 3. So, you could leave it as an alternating series if you wanted to. Or you could just use the alternating series test. There's usually more than one way to skin a cat for some of these problems. Other questions? Somehow
Did
I
you
don't.
do
Yeah.
11, the
Yeah.
1 over n factorial?
And did it say you had to use one particular thing or another?
Yeah, I couldn't find something to compare it to for the direct comparison test.
Okay. So one thing you can, there are a few things that are kind of like staple things to use. 1 over n, 1 over n squared, 1 over 2 to the n. Now remember, this diverges, right? Okay, or you could use a geometric series. Well, that is a geometric series right there, or you could use any other geometric series that converges. And all you really have to say is that since let's say we use this guy, okay? After we get past 2, and now we're at 4, right? 3 factorial is 6, 6 and 9. And then at 4, it's 24 and 16. At 5, it's 120. And now you're at 25. So once you get past a certain point, beyond n greater than 4, 1 over n factorial is smaller than 1 over n squared after you get past a certain point. You see? And since this guy converges, he must also converge. So if you were to look at their graphs, for example, you've got you'll have n squared, and you'll have n factorial, and you see after a certain point, it's below it. Others? Okay. All right, so I want to dip back to the alternating series for just a second. And I want to talk about 2 vocabulary terms, things that are absolutely convergent. One second, guys, I do have to take this. Sorry, guys. Absolutely convergent and conditionally convergent. Absolutely convergent means that better way to say it. it doesn't, basically it doesn't matter if it's got a flipper on it or not. Um, um, so a series is absolutely convergent if, when I take the absolute value, meaning basically knock off any flipper, and it still converges. Okay, give you an example. Something that is absolutely convergent is that guy. He's absolutely convergent because if I knock off the flipper, this guy still converges. Okay. Remember how I was saying that alternating series is like very forgiving and very flexible? Like all you need to be doing is getting smaller in order to work with the absolute with the absolute value. Sorry, with the alternating series. Well, some things will converge even if they don't have that flipper on it, like him. A flipper absolutely is going to make it converge. But then there are things that are conditionally convergent. And something that's conditionally convergent, so do we know of a series that only converges if it's got a flipper on it? So it basically always diverges, but if I put a flipper on it, it will converge.
Harmonic series?
Yes, the harmonic series. It's the classic example. The alternating harmonic series versus the harmonic series. This converges, this diverges. So let me tell you that alternating series, I mean, like you have to grow in order to not converge. I mean, like, and almost everything gets smaller in this game. Okay, very little doesn't get smaller. So a lot of things will converge under the absolute under a alternating series test, but they might not necessarily converge without it, without that flipper. Okay. Okay. So these are just some just some vocabulary. Now, I don't want to go into the limit comparison test yet. Ratio test, that's fun too. Okay. Where is my, nope. Way too much fun. All right. Let's see about radio. I don't think it's in this book. Okay. Let's talk about this for example. We have another, let's talk about vocabulary here. Oh wait, well, we need to ratio test first. Shit, we can't do that first. There's like 7 or 10 different tests The question is which ones do we do first, second, and third? Because they rely, some of them rely upon each other, some of them don't. But my favorite, and this is my personal favorite, is the limit comparison test. Not to be confused with the direct comparison test. Different, okay? The limit comparison test is really powerful. In fact, let me get a good set of examples for the limit comparison. Where are you? I just saw it. It was in my notes. Damn it. I'll use the example we did a minute before. N all over square root of n squared plus 1. All right. When we looked at this a few minutes before, we went ahead and did some algebra on it in order to try and get it to something that would basically fall apart. Okay. Now, when we did all of that, we came up with the fact that the limit of this went to 1. Well, one thing that's quite interesting that you can do is if you take the limit as n approaches infinity of the numerator, I'm just going to call it a to the n and b to the n, okay? Ooh. Okay, time out. This guy, I'm getting ahead of myself. The idea behind the limit comparison test is that you're going to look and see what happens in your head. Just do a quick little thing. As this thing gets bigger and bigger and bigger and bigger, does that plus 1 mean anything after a while? Not really, right? And then basically it's going to fall down to look like something like this, which is that, right? Okay. So what this does is this allows us to say, as I go farther on down the road, I'm approaching 1, right? Well, the way you do it, let's take an example about this one. Limit comparison test. Let's do 2 to the n minus 1. Okay. This guy, if I keep going and going and going and going, what does he eventually look like? Like, what function does this thing begin to look a lot like when I have a billion terms?
1 over 2 to the
Right. It sure as hell looks like this, right? Now, does this converge?
Yes.
Okay. So here's what we do. We compare these two. Now, if the ratio, so if we take the limit as n approaches infinity of 1 over 2 to the n all over 1 over 2 to the n minus 1, okay? So first things first, the first thing you do is you kind of just explode everything until, to get rid of your little itty bitty terms that don't mean squat. Okay? Once you've gotten rid of the little itty bitty terms that don't mean squat, you divide the two. Okay? And this goes to 2 to the n minus 1 all over 2 to the n, which is the limit as n approaches infinity of 1 minus 1 over 2 to the n. Okay? And then once we take the limit, it goes to what?
1.
1. Now, here's what the limit comparison test tells me. It says, now, by the way, this was convergent. Okay. Formally, it's saying that if the limit as n approaches infinity of a to the n over b to the n goes to a number, not infinity, a number that's greater than 0. So 0 is lousy and infinity is lousy. Okay, or negative infinity as well. So, okay. If this is true, then either they both converge or they both diverge. So what this is basically saying is, if I know, like, let's think about it, like, think about it in terms of speed, okay? Think about these two things in terms of how fast they grow, okay? This guy and this guy are both growing at the same speed. Does that make sense? Because of this 2 to the n term. Taking away 1 doesn't make it smaller. It just makes it a little bigger. It just moved it up a little bit, or actually moved it. It moved it to the right a little bit. Okay, but it didn't make it go faster. 1 over 3 to the n would be slower. You see what I mean? Like, this changes the speed, but just knocking off that -1 doesn't change the speed. So I'm looking at how fast each of them is moving. And since they're both moving at the same speed, I can say that he's going to converge and this guy is also going to converge. So, like, think about it like a race, okay? You've got 2 rabbits that are on a racetrack. One of them gets a 10-foot head start. They're both going to finish the race 10 feet apart. See, they're both going, they're going to behave identically. That's why you first find out what he's going to converge to, and then you compare them. And if you get a number, you're golden. Now, if you don't get a number, if you get a 0 or an infinity, then you can't use this test and you have to use something else. Okay? So let's do some examples. I love the limit comparison test. It's definitely a lot of fun. Okay. So blow this thing up in your head. What will it eventually look like? Christine.
4 over k to the third.
Right. Because that -2 does nothing almost, right? Does a little bit in the beginning, but it does very little at the end. Okay. And now we divide them, and shouldn't matter which way we divide it, this over this or that over that. That doesn't really matter, because, let's say it converges to 7 if I did it this way, but if I did it the other way, it would converge to 1/7. Okay, so it's still a number. So it doesn't matter what the order of division is. Okay. Double rainbow it. Now what the hell do we do? So in your head, what's going to happen when we blow this thing up to 1 billion? What's it going to look like? It'll be 1 billion cubed over 1 billion cubed minus 2. What is that?
It's pretty close to 1.
Yeah. If you've got $1 billion and I've got 999,999,998. If you wanted to be a prick, you could have bragging rights, but basically we both have the same amount of money. You see what I mean? Now, how do I show that? How do I show that when this limit is taken, it goes to what we believe is going to be 1? How do I get rid of all of this without just making some magical, mystical math?
If you do L'Hopital, it'll just cancel out and become 1.
Yeah, you could use L'Hopital's rule 3 times. Absolutely. Or actually, if you use L'Hopital's rule once, it would work. You could also do this without doing calculus, because I saw how good you guys are taking derivatives nowadays. Mm-hmm.
You just started with.
What's that?
I said you could have started with the two things flipped, so they're reciprocal, and then so you could split up the fraction.
So if you did it the other way around, I can't split up my denominator. But if I had done it upside down, I could have split up my denominator. I could have split up my numerator. And you would have gotten the same thing. But the point is that now you're going to get 1 all over 1 minus 2 over k cubed. And when you take that limit, as this goes to infinity, this goes to 0, and you wind up with 1 over 1, which is 1. So now this, we should have said in the beginning, does this converge or diverge?
Converge.
It does converge. In fact, there's a way that we can do, again, like I said, there's so many different tests. You either know them all, or you kind of have to work your way around until you eventually learn them all. You can say that this is a convergent, what is called a convergent P series, but I was going to talk about that later. But this converges because it's always smaller than 1 over k squared, right? You could use the direct comparison to show that that converges, right? Okay. Let's do another one. All right. All right. when you get an answer, either tell me it converges with a thumbs up or diverges with a thumbs down. Or I have no idea, which is a sideways thumb.
Wait, can you say that again?
Up converges, down diverges, and who knows, and I don't have no idea, is a sideways. So, Maria, what happens to this thing as n gets really, really big? What does it eventually look like?
It eventually looks like 2 to the n over 3 to the n.
Okay. Now, does this converge or diverge?
It converges because it's a geometric series with an r less than 1.
Right. So, which one did you do? Left over right or right over left? Ryan, what did you use? Left over right or right over left?
I used right or left.
Okay. So far, so good. Has everyone got all that stuff? So those go away. Now what happens? I should be saying limit. What happens when I take the limit?
Term goes. The right term goes to 0.
So it goes to 1. So my question is, does it converge or diverge?
Converge.
Yeah. Because this converges, and it goes to a number that's not 0 or infinity. So it converges. Okay. This is fun. So Connor, what happens when I take this limit? What does this go to?
They go to 1.
And what does the limit of this go to?
I am not sure.
Well, think about this. My denominator, my k in my denominator just got huge.
All right. So would it be 0 then?
The whole thing or just this fraction?
Just the fraction.
Okay. So I've got 1 minus 0 and the cube root of 1.
So just 1 then.
So this goes to 1.
Gotcha.
Okay, so does this converge or does this diverge?
Converge. Maybe.
That's a good question. Let's do this to it. Let's ask ourselves that question. Now, as far as the 3 and the 4 are concerned, I don't give a crap.
Wait, how do you go from 7 and 3 just to k? Wouldn't it be k to the 4th?
Yes. Okay. Now, there's one series that you need to know before you go any further, and that's what's called a P series. Um, so all of these converge, but that does not. That does not, because that's a 1/2, right? All of these diverge, but all of those converge. I don't know why the book did limit comparison before doing P series. P series usually done earlier. Anyway, so does this converge or diverge?
Converge.
Why?
Because if you strip it off, you just see the n 4/3.
Yeah, the exponent is 4/3, and that's bigger than 1. So this converges. Okay. Good question, Ryan. Take this back up here. So this is just a constant, and I don't really give a crap about it, right? It's just a constant. And then basically what I'm looking at is 1 all over k to the 4th to the 1/3, which is 1 all over k to the 4/3. So it is a convergent P series. Okay. Do one more. Let's look at this, since we were talking about it a little bit earlier. What happens as k moves down the road? What happens to that numerator?
It oscillates between 1 and -1.
Yeah, the sine function and the cosine function oscillate. They up and down between 1 and -1. So what does this sort of kind of look like?
1 over k to the 3rd.
But it oscillates between 1 and -1, right? So
Alternating,
what's that?
alternating series.
It starts looking like an alternating series, doesn't it?
Mr. Ronco, would you put a pi next to the k?
If you wanted to, but I mean, then it would. Well, actually, if you put a pi next to the k, then it would always be 0.
Yeah.
Yeah. But if it was a cosine, then it would be pi k, and then it would be between 1 and -1. But this takes all values between 1 and -1, right? You know, there are values that are going to give me a half, you know, like pi over 3. When k is pi over 3, this is 1/2, you know, and so on and so forth. So this guy wobbles up and down. So this looks a hell of a lot like an alternating series test, an alternating series, right? So what you can say is that the sine of k all over k cubed plus 1 is always going to be less than or equal to or we can say that, oh, wait, I don't even need that. I can just put an absolute value on it. Now, tell me, does this guy converge? How would you prove that this converges?
By the limit comparison test.
You could, absolutely. Or the direct comparison test. Or, I mean, you could direct comparison it with k cubed or limit comparison it with k cubed. You see? Either way. But the point is, this converges. Why does this converge?
P series.
This is a P series with P P greater than 1. Sometimes you see it as 1 over n to the P. That's why they call it a P series. I used an A. It doesn't matter what it is. P is greater than 1. So now the question is, does this converge?
Yeah, because by the direct comparison test, it's less. And so if the P series converges and this sine of k or k cubed plus 1 is smaller than it always, then by direct comparison test, it converges as well.
Is it absolutely convergent or is it conditionally convergent?
Absolutely, wouldn't it be?
Why?
Because even if it's a -1 or a 1 on the top, it's just going to keep getting smaller and smaller.
Go back to the definition of absolute convergence. We wrote it down at the beginning of the class. Absolute convergence said um, so by putting the absolute value on there, you're basically killing off the sign, because this now the sign is only going between 0 and 1, right? So this guy and this, so does this converge? Right, this converges. So is this absolutely convergent or conditionally convergent? Look at your definition. The vocabulary is a killer.
Absolutely convergent.
Yes, this is absolutely convergent. Because if I strip off my flipper, I still converge. And the sine function acts like a flipper. It's not a 1, -1, 1, -1 kind of a flipper. It's more of a 1, -1, 1, -1 back and forth between all the values in between. Okay. But it's still flipping. Converge or diverge. Use whatever test you like. When you get an answer, put it in the chat. We'll have a little conversation. So what tests do you guys use?
I did direct comparison with the harmonic series because after 4, it gets bigger.
The problem with the direct comparison is that this is always bigger than the harmonic series, right?
But doesn't that mean it diverges too?
Okay. So you're saying that 1 all over n minus 3 is greater than 1 over n, right? And since this diverges, this must also. That's what you're saying? I agree with you. Who used another tool? What'd you use, Redvic?
Limit comparison.
You used limit comparison? And what did you compare it to?
Harmonic series as well.
Okay, what went over what?
1 over n, 1 over n minus 3. And that the limit of that is 1 as that it approaches infinity. So since a number over 0, they both have the same convergence status, and
Mm-hmm.
the harmonic series diverges, this also diverges.
Good. Good. All right. So, you guys have a 3-day weekend coming up. I'll send you some stuff to work on. Kind of a mixed bag as of now. All right, little alternating series, a little direct comparison, maybe a few P series in there. Just kind of mixed bag it. Okay. All right. Scale of 1 to 5. How do we feel? Put it in the chat. Private chat. Very cute, Lauren. She put in pie. Very cute. All right, cool. All right, get the heck out of here, guys. I'll see you all next week.
See ya.
See ya.